Have you ever really thought about how you'd teach a robot about the real world? And I don't just mean how to see a chair and know it's a chair. I mean, how do you teach it about physics? Well, that's exactly what NVIDIA is tackling with its Cosmos platform. And honestly, it's pretty mind-bending. They're basically trying to build a digital reality, kind of like the Matrix, but for training the next generation of AI.
So let's just start with the biggest question, right? The one that's at the heart of this whole thing. How do you actually teach a machine about gravity, about friction, about what happens when you accidentally knock something off a table?
And here's the real kicker. How do you do all that without the robot constantly breaking stuff? Or even worse, the robot breaking itself? I mean, real-world trial and error is a complete non-starter. When your student is a 2-ton self-driving car, you can't just say, oops, and hit reset.
This entire challenge, this whole puzzle, is what researchers in the field call the physical AI problem.
So what even is a physical AI? Well, the simple definition is any AI that has sensors like cameras or LiDAR to see the world and actuators, things like robot arms or the wheels on a car, to actually do stuff in the world. We're talking about any machine that needs to physically move through and manipulate our reality.
And this right here, this is why we're not all living like the Jetsons just yet. Trying to train these physical AIs in the real world is a massive, massive bottleneck. For one, it's incredibly slow. It's expensive. You need all this hardware. It's obviously dangerous. And maybe the biggest problem of all, it's just not scalable. You can't possibly test for every single weird thing that could happen, like a kid chasing a ball into the street on a rainy night.
Okay, so if training in the real world is the problem, what's the solution? Well, this is where things get really cool. The answer researchers are zeroing in on is to build a world model. The best way to think about this is as a digital twin of our world. The idea is to create a perfect simulation, a place where an AI can learn, practice, and make millions of mistakes without any real-world consequences. It's literally a flight simulator, but not just for planes, for everything.
Now, the official term NVIDIA is using for this is a World Foundation Model, or WFM. The key thing to understand here is that this is not just some static 3D video game world. It's a predictive model. It looks at the world as it is right now, you give it an action, like a robot arm pushing a block, and then it generates what happens next. It predicts the future.
That sounds amazing. Almost like science fiction, right? But how in the world do you actually build a digital version of reality? Let's pop the hood and see how NVIDIA's Cosmos platform is pulling this off. It really boils down to 3 major steps. First, you need an absolutely insane amount of video data. Just tons of it. Second, you have to find a way to make all that video understandable to an AI, a process they call tokenization. And finally, you feed all of that processed data into the model to let it learn the fundamental rules of how things move and interact.
And when I say an insane amount of data, I am not kidding. The Cosmos platform started with 20 million hours of raw video. To put that in perspective, that's more than 2,200 years of footage if you played it back to back. From that ocean of data, they carefully selected about 100 million high-quality clips. The scale is just staggering.
Okay, that next step, tokenization, is absolutely critical. You can't just feed raw video pixels into an AI. It's way too much information. So a video tokenizer acts like this super smart compression tool. It takes all the rich, dense information in a video and turns it into a compact sequence of meaningful tokens. The analogy here is perfect. It's like turning a 2-hour movie into a short, efficient book that an AI can actually read and learn from.
So once your data is in this book format, there are a couple of different ways you can actually build the simulation. One path uses diffusion models, which you probably know from image generators like DALL-E or Midjourney. They basically start with a bunch of random noise and then sculpt it into a coherent video. The other path uses autoregressive models, which work a lot like ChatGPT. They generate the video one piece at a time, constantly predicting the very next word, or in this case, the next token in the sequence.
So the AI has learned from all this data. It has a general idea of how the world works. But how does it go from knowing basic physics to, say, knowing how to perform a very specific robotic task? Well, this is where this brilliant 2-stage training idea comes into play.
This 2-stage approach is really the secret sauce. In stage 1, pre-training, the model learns the general rules of physics from that massive, diverse video dataset. It becomes a generalist that understands the world broadly. Then, in stage 2, you can take that generalist model and fine-tune it on a much smaller, specific dataset for your exact task. This turns it into a specialist, like a digital twin for one specific robot or one specific car model.
I love this analogy because it just clicks. The pre-training is like giving the AI a PhD in general physics. It knows all the theories. The post-training, the fine-tuning, is like sending that physicist to medical school and residency to become a world-class surgeon. It's an incredibly efficient way to get expert performance without having to start from zero every single time.
All right, so we've got this powerful, specialized world simulator. What's the payoff? What can we actually do with this? Let's get into some of the incredible applications this technology is already starting to unlock.
First off, you can generate fully navigatable 3D consistent worlds from a single image. Think about that. You can feed the model one picture of a room, and it can generate a video of what it would look like to walk around inside that room, looking left, right, up, down. It's like having the power to step inside a photograph.
For robotics, this is an absolute game changer. Imagine a factory robot that can think before it moves. It could run thousands of mini simulations in a fraction of a second to figure out the safest, most efficient way to pick up a delicate object. This could unlock a new era of precision and safety, from manufacturing all the way to robots exploring Mars.
And of course, the big one, autonomous driving. These world models are the ultimate simulation engines. You can train a self-driving car on millions of simulated miles, throwing every bizarre, dangerous, one-in-a-million scenario at it, things that would be completely impossible or just flat-out insane to test for in the real world.
And look, this isn't just theory or a cool idea. The results are already here, and they are dramatic. This chart shows how well the generated videos maintain 3D consistency. Basically, do they feel like a real, stable space? The previous state of the art, a success rate of about 4.4%. With Cosmos, it jumps to over 62%. That is not an incremental improvement. That is a massive breakthrough.
But even with these incredible results, the researchers themselves are quick to put things in perspective. They state right there in the paper, and I quote, "The world foundation model problem is still far from being solved." So as exciting as this is, it's a huge milestone, but they see it as just the beginning of a much, much longer journey.
What we're really seeing here are the first concrete steps toward creating true, high-fidelity digital twins of our physical world. And that leaves us with a pretty profound question to think about. If we can truly simulate reality, what's the next thing we should build?